Okay, good morning, everyone. Today we are very pleased to host Ozan Şener, who is a research scientist at Intel Labs. I think I first met Ozan at ICCV 2015 when he was a visiting PhD student at Stanford University, following his advisor Ashutosh Saxena's move there. After he got PhD degree at Cornell University, he was a postdoctoral researcher at Stanford AI Lab, working with Silvio Savarese. And he has done a lot of interesting work in both machine learning and computer vision. And today he will present their theoretical analysis of meta-learning and multitask learning objectives, which are commonly used in many different deep learning problems. Thank you, Ozan, and the stage is yours.
Thanks for inviting. It will not be. Thanks for the inviting. It will not be only theory. It will actually be at most like 30% theory. Most of them to be empirical and interesting analysis. Yeah. So I want to talk about transfer learning and what are the underlying trade-offs of transfer learning. What are the things that maybe matters to practical applications and are more like in practitioners. So if you are doing machine learning, typically what you want to do is you just want to learn a function which converts something into something else. So for example, if you want to do object detection, what you are doing is you want to find a function which converts an input image into a set of bounding boxes. If you are doing robot learning, you want to convert the input image into a set of actions. If you are doing speech recognition, you want to convert the input waveform into sort of a natural language. So if you are doing this searching a function, so the way to search this function is starting with defining a parametric family, such that our functions are defined within this family in terms of some numerical values. This can be a neural network, for example. And then in order to find this function, we need to define a concept of a risk or loss or reward. And then what we hope is we want to find a function or parameters of the function such that its expected risk or expected loss will be minimum when I apply this function in some unknown environment. Unknown in the sense that some fixed distribution. But since I cannot solve this problem, I convert this problem of finding a minimum population risk into the problem we call empirical risk. And empirical risk means that I just do some Monte Carlo sampling about this environment, about this data, and I just compute the average loss or average risk and just minimize this. And this is largely successful, but the question is, what separates success and failures in such a setting? And this has been the topic of study in machine learning or machine learning theory for many years. And the way we study this, we actually look at the error that we introduce by making each sentence, by making each assumption, by talking about each setting, each constraint. So once you go from finding an arbitrary function to finding a specific function within a parametric family, you define a modeling error. It means that now instead of find a perfect result, so a perfect function, we can only have the best function which is representable by a neural network or representable by a transformer. Then once you define all those functions, now you have an error due to the loss landscape. So the best solution you can find is the optimal solution of this loss landscape. Then of course the next point is, once you go from this population risk to an empirical risk, the best solution you can find is the ones minimizing the training error, not the ones minimizing the expected error. So in reality, this modeling error is typically fine because we know that our neural networks are universally approximate and all this nice theory about it. The loss landscape is typically fine because domain practitioners, domain experts know how to define these losses. But the issue is the going from population to the empirical risk. And this is an issue because of two possible reasons. You either fail because you don't have enough data so that this empirical average or training loss doesn't approximate the population average well. And you are still in IID settings, but you are in data scarce setting. Or the second possibility is maybe you are in a world that you cannot actually collect data from your deployment environment. Maybe you will train your autonomous driving in Germany, but you will deploy in Turkey, you will deploy in US. So your setting is non-IID, your test distribution will be different than your training distribution. And regardless of what your problem is, what's your like data scarcity or this non-IID, typically the solution in machine learning way is looking at this multitask perspective. I will use the multitask as an extremely general setting. So I'll call it multitask as long as you are solving multiple things at the same times. It can be multiple data set, it can be multiple loss functions, it can be multiple actual tasks as well. And the reason that multitask might make sense is there's an obvious intuitive reason, which is the world is full of regularities. So if you are solving geometry and if you are solving semantics, they have some underlying regularities because they all are about objects and things. So you hope that things will transfer between them. And even beyond this like intuitive understanding, we have a result from statistics, which is so surprising, it's called paradox, although it is an actual theorem. The Stein's paradox says that if you are estimating parameters of independent Gaussians, and if you have more than 3 estimation problems, and if you solve them jointly, although these problems are entirely independent in every sense, solving them jointly is actually better than solving them independently. And I say that I'll use this multitask learning in a very broad term because once you think like anything which is solving multiple problems jointly is multitask, all these problems becomes multitask learning. The problem of multitask learning, meta learning, domain generalization, continual learning. And all of them are asking very similar questions to each other. Multitask learning is saying that is learning and things jointly better than learning them separately? And meta learning is basically asking, if I am giving a budget of first learning n problems, and if I am required to only be examined after I learn n of them, and if I am only required to be tested on the n plus first one, is learning the n plus first thing easier than learning first n? This is the actual title of the paper by Sebastian Trum from 1985. Is learning the n plus one task easier than learning n? Or we can say domain generalization. Here the idea is I want to learn n things, but I'll not know anything about the n plus one, and I'll not have any adaptation. I just hope that it will work for n plus first one. Or you can say continual learning. Here it's basically saying that learning the n plus first thing should be easier than learning the first n, but you should also remember the first n, so you should be good learner throughout the entire time. So since everything is in a way multitask learning, when you think from this perspective, I think it is better if we analyze it and if we get some good lessons from it and apply to all these problems. The most interesting part that I care about, like recently, and in this talk is, once we talk about this classical learning theory perspective, we move from this perfect to modeling error. And the modeling error basically was saying that the best function you can find within your family. But of course, best you can find means best you can find when you have infinite amount of data points. So you're basically at the infinite data level. But once you go to multitask learning, now you have two-dimensional design space. You have number of tasks in your x-axis, number of data points in your y-axis. The question that answers this learning theory is only for task is equal to number of 1. We understand very well how does the number of data points between 1 and infinity scales. But question is, how does the rest of the entire design space matter? So if you're a practitioner and if you have only budget to increase the task to 1 or increase the number of data points by 1,000, which one should you choose? And maybe more importantly, are the algorithms always better in an entire space, or do we need to design different machine learning algorithms for each quadrant? And in reality, all these quadrants matter. For example, if you're a robot learning researcher, you typically don't have much data, you don't have much tasks as well, because you care about physical robots, deploying them in different environments is hard, deploying them is also hard. Or if you're, let's say, autonomous driving company, you can scale the data, but scaling the number of environments, number of tasks, number of cities, number of countries is not easy. It includes legal issues, it includes much bigger costs. Or you might be in a medical setting, for example, for a single patient, you can get lots of different scanning, lots of different observations, but the scaling the number of patients will be harder. Or you can be a social media company and everything will be easy for you. Then you can have infinite data, infinite tasks, whatever you want. So then the obvious question, what's going on? So how does this space behave? So it will be mainly the focus of this talk. And I'll start with meta-learning because meta-learning is the one that we have good answers. So for meta-learning, I'll describe this entire 2D space. Then I'll talk about multitask learning from a different perspective. And I'll say that multitask learning is inherently a multi-objective problem. And I'll present a multi-objective algorithm which will probably solve this problem. Then I'll, in a hand-wavy way, I'll extend this multitasking learning results to domain generalization. And you can actually see that this thing will extend to continuous learning as well, but it's not in this talk. We have a paper under submission and some archive. So let's start with meta-learning, but if you have questions, it might be good time to ask now, because now I'll get into the details a little bit. I guess not. Okay, so meta-learning is asking these questions. We want to learn how to learn. So we have this set of concept of meta-training and a meta-test. In meta-training, your learner has an access to a collection of tasks. Here is infinitely many tasks. So you are a learner and there is some oracle, let's say in nature, and you can sample as many tasks as you want, and you try to solve them. After this fixed budget, fixed meta-training, the nature will sample a complete new task, and you are required to solve this task as efficiently as possible. So let's formalize it a little bit. So let's say you have tasks, and each task is indexed by gamma. So each gamma is a different task. So each task gives you a different risk function. And since tasks are related, the same solution parameter would apply to each of them. Here you can consider tasks as different data sets. And each task will give me a risk function. In meta-training, I will sample tasks from the task distribution. For each task, I will have an access to something called learner. So if I basically give this learner the task and some meta solution, here it is denoted by theta meta, this learner will actually solve this task and will find a solution for this, specifically for this task. Here is denoted as theta gamma. And of course, the most sensible thing you can do is you want to optimize the average risk over all the tasks when this meta solution is given to the learner. Maybe to make it more concrete, we can consider this meta solution as an initialization of neural network. So let's say I want to find an initialization such that if a different learner for the task gamma starts with this initialization, it will have a low risk or it will solve it well. In the test, nature will sample a complete new task and learner will solve the task. The previous thing that I described was still not computational, not operational. We need to find an algorithm which will actually work in practice. And the one that we consider in this paper is the algorithm called model agnostic meta-learning, MAML. And in reality, the same analysis applies to all of them, but this is the most simple and I think most reasonable one. So in this case, you have a fixed budget of M. So in meta-training, you are sampling M tasks. And then your learner is a practical optimizer with a case steps, actually specific for a single gradient step. What you are doing is, what you want to optimize is empirical meta risk, which is average over M tasks for each task using N samples, such that I use half of the samples to update the learner, starting with the meta solution and finding the solution, and other half to actually optimize the meta risk. Here, the meta risk means that after the learner starts with the meta solution, find this task-specific solution, I evaluate the average over all these tasks, and I can update my theta meta. This is good because here everything is differentiable. So I can do pure gradient-based optimization, and I can actually optimize this meta risk, this meta solution. I mean, this is good, but we did lots of approximation, lots of assumptions. And of course, the question you should always ask, what is the source of error? Where is the error coming from? Did we introduce a new error? And more specifically, what is the cost of all these assumptions we made to go from this idealized setting of meta-learning to MAML? But of course, to answer this, we need to compare this with something else, right? So to say that did we lose something, we have to have a starting point. And starting point is just doing just normal learning, just doing empirical risk minimization over all the tasks you have. So at this point, what we are saying is that let's not do meta learning. Let's just use still sample and training tasks. For each of them, use n samples, but use all the samples, all this data to just find a good solution, which will solve the average task. So I'm saying that I don't want to care about learning to learn. I just want to learn a model which is good in average. So one could argue is this even a meta learning algorithm? More specifically, is learning to n+1 thing is easier than learning to first n? And surprisingly, the answer is yes, and we have a formal proof for this. And since now these are comparable, we can do both theoretical and empirical comparison between them. We call this domain randomized search because so the one focus that we have is reinforcement learning, and in reinforcement learning literature, similar algorithms are typically called domain randomization. So then you can ask, what is the hidden error or hidden cost that we made while defining the MAML objective? So MAML objective looks nice, but it's actually not. The issue is MAML objective is bilevel. So there is this inner learner. So it basically, given an initialization, it optimizes the tasks. And there is outer objective function, which is trying to find the best initialization. So there are two objective optimization problems interleaved in a hierarchical sense. So these kind of problems are called bilevel. And these are exceptional hard problems. For example, even the case of inner problem being linear program, so the outer problem being linear program and inner being convex, which is probably the simplest thing you can imagine, these are still NP hard. So then, of course, the important questions we ask is, while going from this domain randomized search or empirical risk minimization to MAML, we made the costly approximation. We went from the single level optimization to bi-level optimization. So it means that if I have an exact same fixed budget, my error will be much larger. But in the same time, I actually decrease the modeling error because I am modeling this learning to learn problem. I have this hierarchical class structure. I am actually trying to find initialization. My algorithm knows that I am trying to find initialization. So I like to have a low modeling error. So there is clear trade-off between this modeling error and the optimization error. And the question that we can ask is, if I have a fixed budget, which one matters more? So if I have a fixed budget, it means that if I can only afford to use m tasks and n data points per task, which one should I choose and which error dominates the other one? So this is the problem definition. I'll first describe some empirical results and then some theoretical results. But before that, maybe it might be a good time to ask a question if the setting is not clear.
Ozan, I have a question. Why do you call the outer loop initialization?
You can call it anything, but classically in this, when people apply MAML, what they find is initialization of the neural network as an outer loop. So what they do in meta training, they sample different tasks, they find the best network initialization such that when you apply gradient descent for an arbitrary random task, it will perform well. So it's more like this finding an initial point shown in this red circle such that you can jump easily to other solutions.
I have a question as well. So here we sort of like target the n plus first task, right? That's what we are trying to be good at. So can't you like do the same with this? Take the theta of the domain randomized search and just use this theta meta for n plus first. I think that's what we are doing. If that's the case, like, why do we even try to do MAML in the first place?
Yeah, exactly. That's kind of the question that we are trying to ask. Basically, this is a valid solution as well. But the question is, why would you want to do that? I think it might be the case that, for example, if posing this problem specifically will let you find a solution which will be much better. So this solution will be really bad for all the tasks, but somehow it will be good as an initialization.
Okay, so you would do this and then start, individual learners, perhaps.
Yes.
Okay.
Exactly.
Okay. One more thing, is there like any generalizations to further than n+1? Like any considerations of n+2, n+3, n+4, or is it more like, when you have n+1, it's sort of like iterative, n+2 becomes the n+1 of n+1 sort of thing?
So I think, yeah, no, not in this work, because people don't call it meta learning, but I think once you want to do care about n+2, n+3, they call it continual learning, basically.
Okay, thanks.
And like, as you said, we basically want to answer this question. So basically, did we gain anything? So basically, did doing meta learning gain anything in comparing to this using theta meta as a solution? So to answering this is not that easy, because now since we have this 2D space and the definition of something is better than another is also not that trivial. So we start with the setting of MAML, which is mostly used, which is reinforcement learning. And in this setting, you are trying to learn controllers for these simple articulated bodies in a simulator called Mujoko. And what is changing here is typically dynamics of the body or dynamics of the environment. And there are other simulators as well. Here you can actually go beyond the dynamics. And these simulators are, there is a simulator called MetaWorld. And here, not only the dynamics, but also the objectives are changing. You have this simple robot arm in simulation, and you can choose a different goal. And the goals or the type of the goal or the type of the environments are sampled randomly in meta training. The way we ask this question empirically is, so we will look at the entire grid, the entire n by m grid, and we will look at each of the point. And what we do is we will sample k random environments for each, and then we will apply to both PPO-based and TRPO-based MAML, as well as just doing no MAML at all, basically domain randomized search here. We will use time random seeds because the RL is notoriously problematic with the hyperparameters. And then what we will do is we will assume these reward values are actually Gaussian, and then we'll apply one-sided wedge t-test to get the parametric probability that one algorithm is better than other one. And after we getting this probability, we will color this in a way that if the probability of DRS being better than MAML is 1, it will be blue. If the probability is 0, basically it's definitely MAML is better than DRS, it will be red, and anything between with the spectrum. And we will look at this counterplot. So if you do this analysis, it's quite interesting. And it's very nuanced, and it's also surprising in a way. Normally, if you look at meta-learning papers, you see a bunch of good results so that meta-learning works much better than ERM. And it's not the case for us when we do the evaluation in entire space. So in many problems, DRS outperforms MAML or meta-learning significantly so that you don't get anything from doing meta-learning. There are some problems, specifically this Hofschitta and this MetaWorld problem, in which after you reach to some specific sample complexity, after you reach some number of data points and number of tasks, MAML starts to perform well. So the fact that there will be some separation between DRS and MAML, and you will need some really high sample complexity is not that surprising. But I think the most surprising part is these problems from a reinforcement learning perspective are not that different from each other, but the behavior is significantly different. And maybe the most worrying is, if you look at literature, people just choose a single n and single m value and report results. But here we show that empirically, I can choose a different n and m and make any algorithm better than other if I want. So it's actually kind of a problematic that literature stick to showing a single number, although the problem is actually 2D, and there is an entire design space. And of course, at this point, we want to understand theoretically, and we want to say that, can we say anything? Can we basically say something about, to the practitioner, say that if you have this property, this algorithm will work better. If you have this property, something will work better. And we do analysis. There is, in the paper, there's an analysis for the convex case, but I don't find it that interesting. But for the non-convex case, this is the setting. The setting is, we have non-convex functions, and we apply stochastic gradient descent to them. And we apply to stochastic gradient descent to the meta objective for TTR steps. And we obtain these meta solutions. And then we apply stochastic gradient descent for a specific task this time. And we apply it for TTE steps, starting with the meta solution as the initialization. There is, of course, lots of domain knowledge you need to compare them. So we collapse this domain knowledge into a thing we call modeling error, which is shown here and for each algorithms. And it basically means that the risk at the optimal solution. So it means that if you have infinite data to solve the meta objective, how well this thing will behave when in the asymptotic case. So there are interesting objectives you can get from this result. One, the dependency to the number of training iterations and number of test iterations is exactly what you expect. It's square root over t, which is the sensible thing you want in the non-convex optimization. And the rate is same for both algorithms. Two, both algorithms provably meta-learn. It means that you can show that learning the n+1 task is actually easier than learning the first n. It means that with increasing number of training iterations, required number of test iterations always decrease for both problems. So this is interesting because it also shows that I can apply this simple DRS or simple ERM as a provably good meta-learning algorithm. Two, if there is no modeling error difference, so basically if the risk at the optimal solution is same, then we can actually prove that DRS is always better. But of course, this is not the case. And typically, I expect the modeling error to meta-learning to be slightly lower. But of course, at this point, you can actually, as a practitioner, tell these numbers and try to compare them. Unfortunately, that's not easy because these constants are required things which you cannot really compute. It requires lots of geometric information as the curvature of the space. But at least I believe it's a good starting point for future algorithm development and as well as like for practical understanding. So if you go back to this design space of 2D design space of this number of data points versus number of tasks, maybe the answer is if you're at the small budget case, there is no hope. You should not even try meta-learning. You should just do what you would normally do empirical risk minimization, just apply learning, try to find a model which will solve the average task well. If you have a very, very large budget, this idea of like a bi-level optimization makes sense. So you can say that, but it doesn't apply in transfer learning, but it might apply. For example, if you have a budget of development of like 5 years, if you are developing a Mars rover, maybe, because then you can spend 5 years developing your thing, but you have a single shot at test. For anything in between, it's nuance. So I think at this point, if you're a practitioner, you should think about like before applying these ideas. And I think maybe the bigger lessons to machine learning people is you cannot choose the operating point and compare algorithms. If you want to compare two algorithms, you have to compare over the entire design space. Yeah, so this concludes the meta learning part. So if you have questions, might be a good time to ask. Okay. So now we understood the meta learning to some extent from this design space and the sample complex with respect to the data and the task version. So now I'll first talk about general multitask learning. I'll move away from transfer learning and I'll move away a little bit from this generalization. And I'll actually argue multitask learning is not a single objective problem and you need multi-objective optimizer to it. Then I'll present an optimizer we developed for it. And then I'll go back and actually try to extend these ideas to domain generalization. So if you recall, we want to do multitask learning because we hope that solving things jointly is better than solving them independently. And there is like an ongoing theory for it, and you can actually show that it makes sense as well. But if you look at the empirical multitask learning, this was the common picture. What you do is you find this still a parametric class, some neural network, but this time, since you have multiple tasks, your models has some specific structure such that you have shared parameters and task-specific parameters. So I have this HT, which takes an input X. Here, I want to talk a little bit supervised learning way because I think it makes it clear that the label space are separate. It starts with input X and generates different YTs. For example, given an input image, it finds a different segmentation map, it finds a different depth map, or if it finds a different instance segmentation map. And for each task, you typically define a task-specific loss function or risk function, Ri, and then you choose some weights, scalar weights, to actually solve this objectives, and you minimize the weighted empirical risk. This makes sense because this is the most reasonable, straightforward thing you can do. But I will argue the scaling is the wrong solution to the right problem. It's the right problem because we cannot apply optimization to a bunch of different objectives simultaneously because there is no sense of optimality between them. Let's say I have two solutions, two neural networks, theta and theta bar. Let's say one is better in task T1, other one is better in task T2. Which one I need to choose? I don't know which one to choose. So if I scale them linearly or like in some ways, at this point, it gives me the way to choose them, but it's the wrong solution because the question of how are these weights are coming from, what are these weights, is an unknown problem. So we argue the better way to look at it is actually respect the multi-objective nature. Let's say that I want to respect each loss functions, each tasks, and I want to treat them completely separately. I don't want to weight them first. Now I lose the concept of global optimality, and instead I have the concept of Pareto optimality. In Pareto optimality, the idea is basically this. A solution is Pareto optimal if I cannot improve it over all the tasks. In other words, if something is Pareto optimal, improving one objective would require to lose or give up in another objective. And instead of finding a solution over the single utopic solution, what I want to do is I want to find a set of solutions which covers the entire Pareto optimality frontier. So if we go back to the machine learning, if you want to define this formally, we define this concept formally, and idea is basically a solution theta dominates another solution theta bar if it is not worse in any of the objectives, and it is at least better in one of the objectives. And solution is Pareto optimal if there exists no other solution which dominates it. If basically there is no other solution which can improve all objectives simultaneously. Then you can ask, like, how can we find Pareto optimal solutions? This problem looks hard. And if you're in gradient-based optimization, it's not that hard actually. So what you do is you define the optimality for your gradient-based objectives. Here, we will only consider non-convex objectives. And since in non-convex, we cannot have optimality, we can only have stationarity. So we can only have gradient non being 0. We will look for Pareto stationarity. And you can write Kurushkan-Tucker conditions. And these conditions are basically this. If I compute my gradients with respect to the shared parameters, and if I look at the convex hull of the gradients, so basically weighted sum of these gradients, convex combination of these gradients, if the 0 point is within this convex hull, I am in Pareto stationarity. It means that if I can find the right weighting such that these gradients can cancel each other, I am at Pareto stationarity. So this naturally leads to a way to check this optimality condition. What I can do is I can actually try to find the weights, these alphas, such that the norm of the weighted sum of gradients will be minimal. So if the solution is 0 in this optimization problem, then you are at the optimal solution, you can stop. Thankfully, if the solution is not 0, you can actually prove that these alphas are good weights. Good weights in a way that if I do weighted sum of the gradients with this resulting alphas, this direction decrease all the loss functions, or more specifically, doesn't increase any of the loss functions. And this is nice because this optimization problem is not bad, because the alphas are number of tasks, which is reasonable number, and this objective is convex quadratic, and constraints are linear, so everything is nice here. And if you go deep, you can actually see that it's even nicer. So you can apply a Frank-Wolfe type optimizer without any hyperparameters. So there is a trivial way to solve this problem. And what you do is, so you basically look at the task-specific parameters. You just compute those gradients. And then you compute the gradients over the shared parameters. And then you apply Frank-Wolfe solver, which we detail in the paper. And then you compute these weights. And then you use these weights to make a weighted update over the gradients. And this, you can prove that this will lead you to the Pareto stationarity. If you are doing multitask learning, there is a problem here. The problem is, for each task, I need a separate backward pass. And for each task, I need to compute gradients. This is costly. So basically, it means that if I'm solving 5 tasks, my training will be 5 times slower. And we need to solve this because it's a problematic thing. And the way to solve is, look at this, the way that people use multitask learning in literature. The way they use it, they go from this input data X to share the representation Z and to a bunch of solutions. So at this point, we propose an approximation, and the approximation is this. Instead of being finding Pareto optimal, finding the weights in the space of shared parameters, you can find the weights over the gradients with respect to the shared parameters Z instead of the network parameters theta. This is good because with a single backward pass, I can compute all gradients. But then this is an approximation, and does this approximation hurt you? And in reality, it doesn't. And we prove that if you do this trick, you are still guaranteed to reach the Pareto stationarity under very mild assumptions. So before I move to generalization, let's apply to this some interesting multitask learning problems, and let's see, is it working? So one toy problem you always do in machine learning is find the version of MNIST and apply it. So here, there is a multitask version of MNIST. In this case, there are 2 MNIST digits which are overlapped. One is at the left and one is at the right, and they're kind of confusing. And the problem is, given a single input, you want to predict both digits of the left and the right. So to compare them, in this figure, we look at this 2D curve, basically the accuracy of the task 1 and accuracy of task 2. And these yellow lines are if you do a single task solution. So you can actually solve them very reliably. If you do these pink stars, these are, if you try all the possible weights, and if you do weighted minimization, these are the points that you can find. It looks like Pareto frontier, but it's actually not. So if you apply some Pareto optimal algorithm, this is the green one, it actually finds a solution. It solves both of them. But it doesn't improve the tasks. So basically, it's kind of an against the idea of like initial idea that multitask learning will be helpful. But I think it doesn't improve because the tasks are already easy and you have enough samples. And then we apply it to some more interesting problems. Like the one problem is, given an input image, we want to predict semantic segmentation. We want to predict instance segmentation. We want to do depth estimation, disparity estimation. But these are, of course, like kind of an old neural networks and small data sets and everything. And we cannot look at 3D curve because 3D is hard to visualize, but we look at these 2D projections. So all these things actually learning over all 3 tasks, but to visualize them, we look at all these 2D projections. And you can see here now, actually doing naive ERM, so basically naive mixing of the tasks, improve beyond the tasks. We have these pink stars, which are actually much better than the accuracy you get from the single task solutions. For example, the bottom right is depth estimation versus the mean IO for semantic segmentation. And you can still see here, you can apply our algorithm and it finds the better solution. But important thing is our algorithm doesn't find all the Pareto optimal solutions. That's kind of a big limitation. Instead, it finds an arbitrary Pareto optimal solution, Pareto stationary solution. But there were, I think, 5-6 papers in the last 2 years that extended our method to find all the solutions, basically. And you can look at basically this idea of using the approximate version, which is probably a good one. Does it actually hurt? It doesn't. It improves the efficiency significantly. And it even helps with accuracy. We have conjectures, but we don't have actual answers for it, why it doesn't actually help. So yeah, so at this point, it might be good to answer if you have questions about multitask learning, because I'll extend it to the generalization case a little bit.
I have a question, but it might be part of the generalization part as well. Like when you do it on the Z, like I'm guessing that's lower dimensional. Did you check if it's a good representation for other tasks as well, or similar tasks? Like you look at from a representational learning angle?
Yeah,
or is that coming in the generalization part?
That's a good question. So I think like one angle is here in multitask learning, all tasks exist in both training and test. So basically, you know that which task you will solve. So you know that it's a good representation because you're already solving in the training. So you don't need any other constraints or anything else to enforce on it. In generalization, yes, I'll talk about like how to extend to finding good representations, which will generalize to even new tasks. I'll not have answers, but I'll actually at least talk a little bit.
Thanks.
Onur, I mean, I maybe missed some of the parts, but like this Pareto work, we have done also this Pareto optimization, but this is all offline, right? I mean, can you somehow do it online? Am I missing
online?
Something?
You mean in which sense online? Is your data coming online or?
Yeah, data coming online, yes.
This is offline and depends. So I think
because you won't be able to see all the solutions, right? All possible solutions when the data is coming. I guess like if you train your model in advance, then maybe if you have a large, do you understand what I mean? Like if you have a large design space and then you see everything in there, then yes, maybe, but I don't know if it is.
Yeah, I think I understand the question. So I think what happens here is not, we don't want to find all the solutions, so all the Pareto optimal solutions. We only want to find single one, and we want it to be Pareto optimal. So that's why you can apply it online. But in the case that if you want to find all the solutions, bunch of different solutions, cover the entire Pareto efficiency curve, you cannot. You have to start with a solution, basically. So in literature, the way people extend it, they took two directions. They either find an arbitrary solution first in an offline way, using our algorithm. And then starting from that solution, they try to cover the entire Pareto curve. Or they run like many different parallel learning, all offline, independently, but they constrain in a way that they will all find different solutions. They will find diverse solutions.
And that,
but I think
should be computationally quite intensive, I assume, right?
Yes. So basically, if you need to find K solutions in an online setting, you need K times more compute.
Okay, thank you.
Okay. Okay, so I'll try to go from this multitask angle to domain generalization angle. So basically finding good representations which generalize to other tasks or other data sets. It's mostly ongoing work. I'll have only partial answers, and most answers are negative as well. So mostly negative results from now on. So in this generalization setting, people call this domain generalization, zero-shot generalization, all these different kind of things. And idea is sensible. So in training, I want to use as many different diverse data sets as possible. And I want to do lots of algorithmic thing, anything you can imagine. But with the hope that when I apply these resulting models on a test, on a completely unseen and unknown environment, it should work there. So I have a set of tasks, T tasks, bunch of empirical data. All I want is this thing to generalize to the next point. This makes sense intuitively, but I think intuitive sense doesn't cut it. We need some reason to believe that it will work, right? So we need some guarantees that it will work. And to understand it, we need to look at this domain adaptation literature or domain generalization literature. And idea is we have to look at this representation art. So we go from this input X to a representation Z and then the solution Y. An idea is we need to find how this generalization is controlled with respect to this Z space so that we can actually enforce things on this representation space, hoping that it will lead to generalization. And the seminal result, which give you the hope is this, by Ben David, they show that zero-shot test error is upper bounded by two terms. One is your test error in your training data sets, or like meta-training data sets, in this T data set that you collected, plus a term about complexity. Here is the complexity term. Basically, it means that if I choose an arbitrary model, and let's say, if I choose an arbitrary representation function, and if I learn different classifiers on different data sets, the difference between the performance will be different. And the maximum difference between them will be this term, this complexity term, which we call pairwise complexity distance in the calligraphic H, delta H. So I don't want to go into the detail because I'll not present anything theoretical. So basically just think that the hope is I want to constrain the representations enough such that this D term will be small in a way that any model learn over these representations will work similarly over different data sets. And I also hope that when I do this, my test error within training data set will be small. And it actually gives you a nice practical guide to do domain generalization. So basically, the guide is use all your domain knowledge to decide what is the right definition of an invariance for you, so that you can enforce over this representation space. And there are many of them. For example, you can go full adversarial. And full adversarial means that if an adversary only sees your features, only representations, they cannot separate data points from different data sets. Or you can look at invariance risk minimization. And they basically say that if I train classifiers going from representation to the classes differently and independent on different data set, they should give me back to the exact same classifier. Or you can look at our case, which is I want to look at the problems and the Pareto frontier of the different data sets. And I want to constrain in a way that I can only find solutions which are Pareto stationary. So I want my representations to be Pareto optimal. And then what you do is you start from this idealized world, you convert into an empirical definition. If you are an adversarial, you convert into the min-max optimization. And you hope that this min-max will behave well. If you're in IRM, you convert this idea of each data set independently giving the same classifier as a condition on the gradients. If you are Pareto, you convert this to this weighted minimization setting. Next thing is you just solve the constraint optimization. So in the last 1 year, we applied this idea from a practical setting to many problems. One is the semantic segmentation. So we say that maybe there is hope. Maybe the computer vision literature spent 20 years developing data sets, and there are so many of them. Maybe if we use all the data sets, we can learn universal models which will work everywhere so that robotics people can use them, they can be happy, they don't need to resolve perception. So then we collect these 7 large-scale data sets. It includes everyday objects, it includes driving data set over different parts of the world, it includes indoor objects. And then we apply this simple weighted minimization, pure ERM, with equal weights. And it works incredibly well. It's surprisingly well. It works in all over. So we evaluated entirely in zero-shot in a way that these models are evaluated on a data set they have never seen in training. And it performed well, almost at the level that supervised models on this data set actually perform. We even actually submitted to a challenge, wild-dash segmentation challenge. It actually became first and beat the models which use the data without using the data. This is good news, but all the methods failed. All Pareto optimization, adversarial learning, IRM, anything imaginable. I didn't put the numbers because they are really bad. And I think the signal is it doesn't work. The last 10 years of machine learning algorithms doesn't do anything here. Then another friends from the same lab, from Intel Labs, applied this idea for monocular depth estimation. They collected 5 data sets, and then they did learning the ZRM with exact same weights, and it performed well. And when you apply all the methods, they all improved over a year. And actually, this improvement for this multi-objective settings, this Pareto optimization, was very significant. So this is kind of a weird mixed signal, and we said maybe we should figure out the reason. Maybe we should find when does it work, when it doesn't. So I mean, if you're a segmentation researcher, you should be happy. If you're a depth researcher, you should be happy. If you're a machine learning researcher, it's just pure sadness. So then we were getting ready to actually do some large-scale empirical study. Hopefully, people from Facebook did it already for us. And they actually tried almost all the algorithms from last decade on all available benchmark for domain generalizations. And they showed that in all of them, ERM either beats them or performs similarly when evaluated properly. Properly means with reasonable data augmentation and with the reasonable compute and reasonable hyperparameter selection. And this is kind of a negative and worrying result. And one thing we want to understand is why. And I think we can go back to the seminal result of the Ben David. And he basically said that this test error in zero shot is dominated by two terms, right? One is this complexity term. Other one is the best test error that you can obtain within your training data set within the constraint space, within this invariant representation you learn. I think the last decade of machine learning research focused on this complexity term. We try to find very inventive ideas to constraint representations such that it will give us invariance. But no one cared about the other term, which is basically the error that you get over your training data sets within the constraint space. The issue here is, if you can define this invariant space perfectly, it's fine. But we use empirical definitions. We use things like min-max. And we use this definition and we capture this space from data directly. So once this space and constraint space is not correct, you increase training error. And if the increase here is significant, it will actually cause huge error to you. And the interesting thing is, for ERM, there is no issue there. It's irrelevant because ERM is not solving a constraint optimization. It's not enforcing anything over this representation space. And a very interesting result that we can show, hopefully will be on archive in a month or so, is this thing, the part about the error on the training data set, test error of the meta training data set, will dominate the other part if you don't have enough tasks, enough in a sense that number of tasks required should be the interesting dimensionality of the invariance problem. Interesting dimensionality here means this. If you want to be solving, if you want to generalize zero-shot way, and if you want to be better than ERM, if you need number of tasks which are higher than the dimensionality of your nuisance space, all the noise variable, all the background variable and everything. Or for Pareto optimality, it should be higher than the space of Pareto efficiency curve. This is a hard thing to ask, and all these baselines, all these benchmarks I presented, they have 5 or 7 tasks, and typically 5 and 7 is a very small number. And it's also partially explained why it works for that case, because the original authors of the paper did incredible amount of work to constrain the problem in a way. They removed all these nuisance variables as much as possible. They normalized everything. They did crazy tricks. At that point, they actually decreased the dimensionality very well so that they made the algorithm applicable to these algorithms. So maybe, since I don't have much time, maybe we can look at the overall picture first, then I can answer the questions. So if you look at the overall pictures in this 2D space, if you don't have much number of tasks or high number of data points, nothing is practical. At this point, I think you should just stick to ERM. And I think just do sensible things from inducing the invariance, the things that the domain experts can do, and don't get involved with the algorithmic part much. The algorithmic part becomes interesting on these 2 different quadrants. One is the low number of tasks with high number of data points, or high number of tasks with reasonable number of data points. If you have high number of tasks and low number of data points, at this point, if the data is limited, but the number of tasks is abundant, seeking multitask objective is actually better, both empirically and theoretically. Or if you're at the level of this basically small number of tasks but high number of data points, you should definitely use ERM. And we can actually show that it will improve with respect to all the existing algorithms. And if you're in the case that you have lots of data points, lots of tasks, I think at this point, everything is in play. So you can all the existing algorithms, almost everything will work because at this point, most assumptions are actually becomes reasonable from an empirical perspective. So I think that's the main talk, and thanks for it. So I can now answer questions, and all the code and the papers, everything is online.
Thank you, Ozan. Yeah, we are open to questions.
I mean, I asked too many questions, but I had one more. This is not too important, but it's been something I've sometimes thought about more from the philosophical point of view. Like when we are solving tasks, like the metric we are trying to do is not always the same as loss, right? We are using surrogate loss functions to make some other metric better. Could there any be relevance, because I'm guessing the results, we are based on get the losses, but their surrogate behavior might not be good. For example, very simple cross entropy versus accuracy, right? Could the negative results be somewhat explained? Not entirely, of course not, but somewhat due to this thing. Like, could it be relevant? I don't know.
Yeah, that's I think a good question. But unfortunately, no. I wish it was. Then I think it will be much simpler direction, right? Just find a good surrogate objective. But actually, although all the results I showed in terms of the final accuracy, you can plot the validation error, test error in the exact objectives as well. So I mean, there is part which is like philosophical part, which is maybe if we manage to find the better loss functions, maybe these algorithms will work. But I'm saying that even if you evaluated on the test error on the surrogate objectives, the results still hold, basically. It's still negative.
Okay, thanks.
So maybe I can ask a question, Ozan. I think this is mostly related to the meta-learning case, but maybe the others as well. So when we talk about there are some tasks, like for example, in this meta-learning algorithm, you give us this algorithm which first starts by sampling these different tasks, which is done in a random manner. But what about, like, for example, following a curriculum learning type strategy in order to randomly sample these tasks, but maybe in a more ordered manner? Are there?
Yeah, I think this is like a sensible strategy. I think it's a way that you can use to improve both meta-learning and ERM, right? You can use curriculum learning. But I think there are multiple axes, right? There's this axis of modeling error. In this case, you are not changing the modeling. So basically, you didn't touch the model. And there's this angle of how the loss functions behave. You actually change that. So basically, change that your loss is basically first easier, and then it's getting more complicated. But at the same time, sample complex is not about this nature. Sample complex is about how much data points you need to solve this optimization problem. So at the end, it is still bi-level meta-learning. So it will still require a really high number of data points. So although it will improve, I think it will improve both ERM or DRS and meta-learning in the exact same manner. So I think it's a good thing to do from a practical perspective, but I think it will make a difference in terms of choice of algorithms. It's a different axis.
Okay, thank you.
Ozan, you haven't talked much about the continual learning part, but what if you have the data coming, like the hard negative cases, the cases that you fail, where does it fit in this plot of yours, which is like very good summary, by the way?
Yeah, I think continual learning is a little bit much more complicated. The reason is, okay, let me explain in as simple as possible. Here, optimization is mostly fine because all the gradients are unbiased, because you are sampling data randomly. In continual learning, everything is non-stationary. the data is coming in a very non-stationary and a very correlated manner. At this point, we have like one paper on arXiv on like large-scale continual learning for NLP. We submitted another one to CVPR, and both of them actually shows the same thing. The SGD actually fails, unfortunately, for ERM and all this algorithmic setting. And the reason is you have to capture this correlation, non-stationarity in the data, and it hurts generalization significantly. So continual learning is adding even a different axis to it, the axis of trying to find unbiased gradients. And that's the hard problem. From the perspective of generalization and everything, like from this picture perspective, it doesn't make any difference to the MAML, basically. I think all the results actually hold. If you have a bi-level optimization problem, it will suffer. If you have a single optimization problem, it will work reasonably better. And the part about remembering the past is a different problem. It's called core set optimization. So it's basically finding a small set of data set which will summarize all the data you have already seen. That's actually largely solved, and actually you can use those ideas to improve continual learning. So if I was doing continual learning, actually I am doing continual learning nowadays, I would attack the optimization part, because I think that's the hardest part, and that's the part which is causing the maximum amount of error.
I have also a more practical question. Are any of these conclusions affected by the number of tasks? For example, Tesla identified 30 plus tasks in autonomous driving. That means they have 30 different networks or something running together with varying difficulty and training data each, and like incoming data all the time, right? That's the problem they are facing at the moment in the real world autonomous driving application. Do you have any, like, I don't know, experience with the number of tasks growing?
Growing through time or growing in general, being large?
Both, as you see, both the data.
Yeah. So being large, I think it's basically the x-axis here, right? So a basic number of tasks you have or number of data that you have. And I think at the end, it is better to have the high number of tasks for every imaginable way. So you can look at it from optimization angle, it's better. It's actually an easier optimization problem. You can look at generalization. Actually, multiplying the number of tasks is better than multiplying the number of data points. And you can show that as well. So I think, like, from a practical perspective, we should try to solve as much task as possible if you have a way to get cheap label for them. From a perspective of like within this transfer learning, I think it's clear that there are some algorithms which will only work with high number of tasks. And I think unless you reach there, you are solving a completely different problem. So basically, the problem that like academics solving in like with 3 tasks and probably Tesla solving 30 tasks are completely different. And in a way, same algorithms will work differently in both cases. The algorithm A and B, their order can be completely reversed. Because that's the case of these results for like MAML versus ERS and generalization, like all the domain adversarial methods versus ERM, right?
I see. Thanks.
But I also think 30 is still low if you want to apply them, because nuisance variable is the dimensionality of the, just like look at the background space, right? So the dimensionality of the differences between the data sets. So basically, the Tesla, I don't know, like I think collecting data in like 5-6 countries maybe. Actually, Tesla is collecting many more. But basically, whatever left in the table, right? What is the invariance that you didn't capture with the data? That dimensionality should be less than the number of tasks to have any hope.
I see.
Okay, maybe we can have one last question. Okay, it seems we don't have any. Again, thank you, Ozan. This was really an insightful and interesting talk.
Thanks. It's fun.
Thanks, Ozan.